Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the second law efficiency. We defined the thermal efficiency and the coefficient of performance for devices as a measure of their performance. They are defined on the basis of the first law only, and they are sometimes referred to as the first law efficiencies. The first law efficiency, however, makes no reference to the best possible performance, and thus it may be misleading. Consider two heat engines. Both have a thermal efficiency of 30%, as shown in the figure. One of the engines is supplied with heat from a source at 600 Kelvin, and the other one from a source at 1000 Kelvin. Both engines reject heat to a medium at 300 Kelvin. Here, I have one question for you. Do the both engines convert to work the same fraction of heat that they reserve? Are they performing equally well? At first glance, both engines seem to convert to work the same fraction of heat that they receive. Thus, they are performing equally well. When we take a second look at these engines in light of the second law of thermodynamics, however, we see a totally different picture. These engines, at best, can perform as reversible engines, in which case their efficiency would be. Now, it appears that engine B has a greater work potential available to it, and thus it should do a lot better than engine A. Therefore, we can say that engine B is performing poorly relative to engine A, even though both have the same thermal efficiency. It is obvious from this example that the first law efficiency alone is not a realistic measure of performance of engineering devices. To overcome this deficiency, we define a second law efficiency as the ratio of the actual thermal efficiency to the maximum possible thermal efficiency under the same conditions. Based on this definition, the second law efficiencies of the two heat engines discussed above are: that is, engine A is converting 60% of the available work potential to useful work. This ratio is only 43% for engine B. The second law efficiency can also be expressed as the ratio of the actual working output and the maximum possible work output for heat engines or work-producing devices. This definition is more general since it can be applied to processes as well as to cycles. Note that the second law efficiency cannot exceed 100%. We can also define a second law efficiency for work-consuming non-cyclic and cyclic devices as the ratio of the minimum work input to the useful work input. For cyclic devices such as refrigerators and heat pumps, it can also be expressed in terms of the coefficients of performance as. Again, because of the way we defined the second law efficiency, its value cannot exceed 100%. In the preceding relations, the reversible work should be determined by using the same initial and final states as in the actual process. The definitions just given for the second law efficiency do not apply to devices that are not intended to produce or consume work. Therefore, we need a more general definition. However, there is some disagreement on a general definition of the second law efficiency, and thus a person may encounter different definitions for the same devices. The second law efficiency is intended to serve as a measure of approximation to reversible operation, and thus its value should range from 0 in the worst case to 1 in the best case. With this in mind, a more general definition of the second law efficiency of a system during a process is defined as. Therefore, when determining the second law efficiency, the first thing we need to do is determine how much exergy or work potential is expended or consumed during a process. In a reversible operation, we should be able to recover entirely the exergy expended during the process, and the irreversibility in this case should be 0. The second law efficiency is 0 when we recover none of the exergy expended by the system. Note that the exergy can be supplied or recovered at various amounts in various forms, such as heat, work, kinetic energy, potential energy, internal energy, and entropy. Sometimes there are different opinions on what constitutes expended exergy, and this causes different definitions for second law efficiency. At all times, however, the exergy recovered and the exergy destroyed must add up to the exergy expended. Also, we need to define the system precisely in order to identify correctly any interactions between the system and its surroundings. For a heat engine, the exergy expended is the decrease in the exergy of the heat transferred to the engine, which is the difference between the exergy of the heat supplied and the exergy of the heat rejected. The net work output is the recovered exergy. For a refrigerator or heat pumps, the exergy expended is the work input, since the work supplied to a cyclic device is entirely consumed. The recovered exergy is the exergy of the heat transferred to the high temperature medium for a heat pump, and the exergy of the heat transferred from the low temperature medium for a refrigerator. for a heat exchanger with two unmixed fluid streams, usually the exergy expended is the decrease in the exergy of the high-temperature fluid stream, and the exergy recovered is the increase in the exergy of the lower temperature fluid stream. Okay, that's all for this task. Thank you very much, and see you next time.